ಬಂತು ಬ್ರೋ.
Hello, good morning, all of you. Hello, I am audible. Hello. Today, yes, good morning, all of you. Today's seminar is snow sensors and transducers. Today topic is very much more interested and related to legal metrology. And today our scientist is, has a loads of experience in the field of sensors, meteorology. Sir has completed BTech in Electronics and Communication from NIT, and MTech is also from NIT, and sir has also completed PhD in improving speech intelligibility with digital signal processing technique for speech processing. And sir has published loads of papers in the field of meteorology. And sir now presently had an additional director, R&D Center, Defense Geoinformatics Research Establishment, Defense R&D Organization, Manali. And sir has a project management expert with 20 years experience, having an explanatory track record of planning and implementing high value technical project in the domains of geoinformatics, sensors, instrumentation, automation, calibration, and non-conventional energy system. And I am requesting to sir, please continue this session.
Thank you. Thank you very much for a kind and generous introduction from my end. I hope I am audible to everybody.
Yes, sir. Yes, sir. You are audible.
Okay. So I am really sorry because earlier my topic of the presentation was metrology for metrology, but due to some unavoidable circumstances, I had to change my topic. But what I assume is this topic would be more interesting for you and also new because we are the only organization who are working in snow and avalanches in Southwest Asia. So probably whatever information and knowledge what I'll be sharing with you would be very, very exclusive to the snowbound areas, and especially it would be very helpful for the meteorology also, because these kind of things nobody else is doing, nobody else is developing such kind of sensors and instruments what we are doing for avalanche prone areas. I have a presentation in which I'll be covering various aspects, right, starting from the measurement, the details of sensors and transducers, and last but not the least, I'll be sharing few aspects regarding the avalanche safety, rescue, and other things also. So if everybody is ready, can I start the presentation?
Yes, sir.
I hope the presentation is visible to all.
Yes, sir. Visual.
Can you see my screen shared?
Yes, sir.
Okay. Good morning, everybody. On a joyous and sunny Saturday at my end, I would all welcome you to this webinar, which topic is snow sensors and transducers, introduction to snow and avalanche hazards in Indian Himalayas. I am Neeraj Sharma. I am basically working as a scientist F and joint director in Defense Geoinformatics Research Establishment, Defense R&D Organization. Before 2020, our lab was known as SASE, which means SASE, which stands for Snow and Avalanche Study Establishment. But after merger of two labs in November 2020, we were rechristened as Defense Geoinformatics Research Establishment. And our umbrella was widened, in which we would look into all the geo hazards in addition to snow and avalanche hazard also. But in the present presentation, I'll be limiting myself to snow and avalanche hazards in Indian Himalayas only. A brief outline of the presentation, if I start with, I will start with the basics of sensors and instrumentation, then getting into insights of hazards and disasters in Indian Himalayas, natural hazards in Himalayas, snow, snowpack, and avalanches. What are they? Types of avalanches. Snow avalanche study establishment. What is the vision and mission of our lab? Then snow specific sensors, what indigenous development we have done in these sensors, and finally coming to the avalanche safety and rescue operations, what we are ongoing. So most of us would be knowing, but just to give you a brief, difference between the transducer and the sensor. A transducer is basically a device which transforms energy from one type to another, even if both energy types are in the same domain. While a sensor or an actuator, a transducer can be finally divided into sensors which monitors a system and actuators which impose an action to the system. So the bigger umbrella is the transducer and sensor oblique actuator is the subset of the transducer. Various types of sensors which we use in our smartphones are temperature sensors, color sensors, humidity, proximity, touch sensors, gyro sensors, magnetometers, etc. So sensor system as a whole is a bigger subset. Inside it, we have a sensor. Inside that, we have a sensing element or a transducer, which actually gives us the application. So a physical medium like the temperature is a stimulus. The stimulus is given to the sensing element, which is maybe resistance. Then for an RTD maybe, then the output is taken in the form of a voltage. The conditioning is done and the target handling is done as an information to the source. So sensors, as a definition, sensor is a device for sensing a physical variable of a physical system or an environment. So as you can see in the figure, a device that receives and responds to a signal stimulus is a sensor. So the valve as on date is the actuator, while the sensor is the eyes of a human who is just watching this water level there and actuating the valve. Sensor actually needs information which can be processed and finally given to actuator to have the physical stimulus or control over a quantity. So sensing mechanisms are there. There are sensing devices, then comes to the sensor systems, and finally it gives a measurement and control systems. So from top to bottom is a transition from science to engineering. From bottom to top, it is a transition from information sensor, which needs information. The classification of sensors, it can be done on the basis of physical quantities which they measure, the mechanical quantities like the displacement, strain, rotation, velocity, acceleration, pressure, force, twisting, weight or flow, thermal quantities like temperature and heat, then electromagnetic optical quantities like voltage, current, frequency, phase, visual images, light, magnetism, and chemical quantities like moisture, pH value, other different quantities. This is the basic classification. This can be furthermore, it can have different type of categories depending upon what we are trying to measure, which physical quantity we are trying to measure. Transducer is a device that converts the primary form of energy into a corresponding signal with a different energy form. So basically converting energy from one form to another is the part of the transducer. Primary energy forms are mechanical, thermal, electromagnetic, optical, and chemical. It takes form of a sensor or an actuator when it actually acquires information from the real world and it detects a signal or a stimulus. Actuator, a device that generates a signal or a stimulus. So real world, it's sensed by a sensor. Intelligence system gives the feedback. It gives you the actuator, and finally the stimulus or the correction factor is applied to the real world mechanism. Now coming to the electronic sensors, because these are the most widely used sensors these days. It converts a direct parameter or a specific real world stimulus into a measurable signal. Generally, electronic sensors are primary transducers, which changes real world parameter into electrical signals, or a secondary transducer, which converts an electrical signal into analog or digital values. So real world and analog signal, we have a primary transducer. Between the analog signal and the usable values, what we want to have for a system, we have a secondary transducer. Typical electronic sensor system, we have an input signal, which is also called the measurand, which is given to a sensor. Sensor gives an analog or digital signal as the data, which is given to the microcontroller, which processes the signal and gives the communicated in a communicable form, and finally into a network or a display or a measurement system, whatever is there. Various examples of electronic sensor systems. Components may vary as per the application. A digital sensor with an instrument is a microcontroller, a signal timing, and a data storage. As given in the block diagram, we have sensors which are connected to a microcontroller, a signal timing memory, a keyboard, and a display, which is a handheld unit kind of a thing. Analog sensor analyzed by a PC, where is a sensor interface is there, in which we have analog to digital converter, communication and signal processing. And then we have a interface like a RS-232 or 485 or a CAN bus, from which it is transferred into a PC through a communication card. Multiple sensors displayed over internet. This is the basic form which is being used these days most of the time. We have a sensor, processor, and a communication unit with a sensor bus connected to a PC with a communication card. And similarly, it is from a PC, it can be sent on internet to various users who can process the data. So coming to the primary transducers, the conventional transducers were large and based on conventional technologies like the thermocouples, which were based on sensing of temperature difference, the compass, the magnetic direction. Microelectronic sensors which come these days are millimeter size, which are highly sensitive, but they are less robust than the conventional transducers, like the photodiode or the phototransistor, which gives us the photon energy or the light, infrared detectors, proximity intrusion alarms, piezoresistive pressure sensors, air or fluid pressures, microaccelerometers, which give us the vibration, the velocity, chemical sensors, which give us the oxygen, carbon dioxide, monoxide, nitrate contents, explosive, etc., and DNA arrays, which match the DNA sequences. On the right hand side, you can see the various forms in which the various transducers, they are converting the different physical quantities into the electrical quantities. Like the light level is converted into the resistance with a photoconductor, which is a light sensitive semiconductor resistance. The pressure is converted into change in capacitance. The photodiode, the change in light is converted into current. Now coming to the instrumentation considerations for the various transducers or the sensor technologies. First, we have to define the sensor technology. Then we have to come into the sensor data collection topologies, how to collect the data from various sensors. Then is the data communication between the various sensors. What about the power supply? The data synchronization, how it is to be synchronized between various sensors which are collecting the data. What are the environmental parameters which we have to think for before applying a sensor, and how to have the remote data analysis, or how to communicate the data from the point of measurement to the analysis part. So in the figure you can see I've tried to explain in the environment, perceptions goes to the sensors, then to the effectors, which gives the corrective actions which are applied to the environment again. So measurement, coming to the measurement, it is basically having an idea about a physical phenomena, which is done with the sensor systems which give a measurement output. So interaction between a sensor and the environment surrounding the sensor is basically the measurement. Compound response of multiple inputs is provided as a measurement output. Different errors, as we all know, there are different measurement errors also, like the system errors, which is due to the imperfect design of the measurement setup and the approximation, which can be corrected by the calibration. Random errors, variations due to the uncontrolled variables, which can be reduced by averaging. Specifications of a sensor. Basic specifications of a sensor include the accuracy, which is the error between the result of measurement and the true value being measured. Resolution, the smallest incremental change a measurement device which it can make. Sensitivity, the ratio between the change in output signal to a small change in input signal. Slope of the input-output fit line. Repeatability or precision, the ability of the sensor to output the same value for same input values over a number of trials when the environmental conditions are not changed. So there's a confusion between the accuracy and the resolution which needs to be resolved. Most of the time these both of the terms, they are being used interchangeably, which is not the fact. Actually, the accuracy gives us the measurement difference between the true value and the measured value, while the resolution is the minimum value of change which can be intercepted by a sensor. In the figure, we can see a sensor which can have a high value of resolution cannot be accurate, while in the other terms, a sensor which is having a low resolution cannot be accurate. So, in case we have a sensor with a high accuracy, it doesn't mean the resolution is, it means the resolution is good. But in case we have a sensor with a high resolution, it cannot guarantee that the accuracy of the sensor is quite high. Accuracy and precision, these terms are also used interchangeably most of the times. So you can see there's a difference between the precision and the accuracy. In the first figure, the results of a measurement are quite precise because they have very less diffusion between dispersion between each other, but the accuracy is very low because the actual measurement and the measured values have a lot of difference. The second figure, you can see it is neither accurate nor precise because there is a lot of dispersion between all the readings, and the readings doesn't lie within the actual target. In the last figure, you can see it is precise as well as accurate because the difference between the measured value and the actual value is low. All the readings, they lie between the target value, and the dispersion of all readings is very less. Coming to some other specifications of the sensor which we have to actually look forward is the dynamic range, which is the ratio of maximum recordable input amplitude to the minimum input amplitude. So it is given as a log value in dB, which actually defines the range of the instrument when we are measuring it in a dynamic environment, which is ever changing. Linearity, which is the deviation of the output from the best fit straight line curve for a given range of the sensor. This is the basic property of the sensor, and linearity cannot be achieved with the sensor because it is a physical, parameter of the sensor. But yes, there are various methods with which we can achieve the linearity by applying corrections to the sensor. Transfer function, which is also called the frequency response, the relationship between the physical input signal and the electrical output signal, which may constitute a complete description of sensor characteristics. Similarly, the bandwidth is the frequency range between the lower and the upper cutoff frequencies within which sensor transfer function is constant gain or it is linear. Beyond the bandwidth, the sensor doesn't perform as per the characteristics given in the range. Noise is the random fluctuation in the value of the input that causes random fluctuation in the output value of the sensor. Now coming to the basic thing, what is a disaster? What is a hazard and how do we deal with it? So I have tried to put in some pictures here where you can see various disasters and hazards and the aftermath, as a tropical floods in Haiti, which came in 2004, tsunami in Indian Ocean in 2004, and various Himalayan hazards also. In the first figure, you can see it is a bigger landslide which is affecting a village. In the last or the second last figure, you can see here it is a flash flood situation, and the last figure, it is a fire situation. So definitions: a hazard, any substance, phenomena, or situation which has a potential to cause disruption or damage to people, their property, their services, and their environment. So there is a potential for an event to occur, and there's a vulnerable area which it can affect. So for a hazard, it is a phenomena situation that has a potential to damage. It has not yet damaged. So in this figure, you can see this is a potential hazard. This stone at this hillock is a potential hazard which can have a disaster in this vulnerable area. So as of now, a hazard is something which has a potential but has not actually done some kind of damage anywhere. So various classifications of hazards are natural hazards, biological hazards, technological hazards, and societal hazards. Natural hazard may or may not result in a disaster, as I actually explained you. It has a potential to finally convert it into a hazard. Natural hazard is a natural phenomenon that can potentially trigger a hazard, which the examples are earthquakes, mudslides, floods, volcanic eruptions, tsunamis, drought, and avalanches. While a normal hazard may be termed as a physical event which need not necessarily result in a disaster. Now, coming to the disaster, disaster is a serious disruption of the functioning of a community or a society involving widespread human, material, economic, or environmental losses and impacts exceeding the ability of community to cope up using own resources. This has been taken from the Asian Disaster Preparedness Center definition. So this definition has various parts. First part says it is a serious disruption of functioning of a community. So disaster cannot be termed as if it's affecting only a single person or maybe a few persons. It is something which is affecting a complete community or society involving widespread. It means the spread is also quite wide. It cannot just happen for few people or one or two people. Widespread human, material, economic, and environmental losses. So the losses can be either human, they can be material losses, they can be economic losses, or they can be environmental losses as well. And the final definition states that the impacts, whatever disaster impacts, it is exceeding the ability of normal community to cope up with own resources. That means the resilience capability of a community to overcome a disaster, overcome something which has happened is can be termed as a disaster. That means in case something happens and a community has the ability to, cope up with that kind of a thing with its own resources cannot be termed as a disaster. So disaster changes which are so great that they may cause damage to the shape of land or to the lives of people or other living things. Great changes happen deep inside the earth and on its surface as well. Common natural disasters are volcanic eruptions, earthquakes, cyclones or hurricanes, cryospheric hazards, floods, droughts, forest fires, or bushfires. So these are the very common natural disasters which occur worldwide, and we have almost existence of all of these natural disasters in India as well. Now I'll be restricting my discussion towards the natural hazards which are most prominent in the Indian Himalayas, since I'm working in this area. We have various meteorological and geological hazards coming with the snowstorms, which is high quantity of snow with lot amount of wind deposits cornices, avalanches, I'll be explaining further, flash floods, rock falls, debris and mud flows, ice falls, crevasses, dam bursts, glacial lakes, and lightning which is happening in these areas. So in the first figure, you can see this is a big time rock fall, you can say, or a landslide which has happened, which has damaged the complete road. This is also one of the landslides which has happened due to haphazard construction in some hilly areas. This is a flash flood kind of a situation. This is a river flood kind of situation. Avalanche showing, landslide again. Then this is kind of a debris or snow flow which has happened, which has caused damage to a building. So coming to the Western Himalayan mountain ranges, which are covering most of the Indian subcontinent. So we start with the first Himalayan range, which is called the Pir Panjal range. It is the first range to which the westerlies or the western disturbances strike, and we get most of the snowfall or the rainfall in these areas because this is the first range the moisture-laden winds strike before going into the other Himalayan. The second comes the Great Himalayan Range, in which the Gurez sector, the Jozila Pass, and these passes comes. The third comes, the third is the Ladakh Range, and fourth is finally the Karakoram Range. The snow belt in the Himalayas, as you can see here, I'll just show you. This is a visual of an avalanche here. The snow belt in Himalayas, it extends right from the Jammu and Kashmir, Himachal Pradesh, Uttarakhand, moving through Nepal, Bhutan, and covering the Arunachal and Sikkim area in India. So in these complete range, we have divided whole of the Himalayas into Western Himalayas, Central Himalayas, and Eastern Himalayas, in which whatever vulnerability of cryospheric hazards is there. So we take into account the road access in Western Himalayas, 11 road access which are affected by the avalanches. There are 6 tracks in Siachen. There are 14 road access in Central Himalayas and 24 road access in the Eastern Himalayas which are being affected. So before discovering anything about the disasters in the cryospheric areas and the Himalayan region, we have to get a brief insight into what kind of a material is snow. So whatever you see in this slide, they are the microscopic representation of various types of crystals of snow which are seen under a microscope. Snow is basically a viscoelastic substance, meaning it can behave as a liquid as well as a solid. So seeing this kind of a characteristic of the snow, we can also term snow as a very complex material, because snow is the one of the materials which exists at its melting point. I mean, at 0 degrees centigrade, which is the melting point of snow, it exists in itself. You can see the fresh snow crystals. This is a microscope view of a fresh snow crystals, which have a very, very low density and a lot of air gaps between them. The second stage of snow, after some time it has fallen, is the round grain crystal, in which the settlement occurs and the density of the snow increases. The third stage in this is the hard depth hoar crystal, in which you can see it has been melted and refreezed again, and the density has again increased. And the final is the subsurface hoar, which is the actual snowpack which develops after 5 to 6 days of snowfall, of fresh snowfall. So coming to the snowpack and how avalanche triggers, snow is said to be a viscoelastic substance, meaning its choice of behavior is determined by the rate of strain. That is, snowpack can withstand a much larger strain without breaking if the load is not applied. A load is applied slowly. Think of as an example, we can think of an elastic band or a chewing gum on a cold day, or other viscoelastic substances. They will stretch if pulled slowly, but if will break if it is rushed. This theory helps to clarify the idea of trigger, which leads to big time avalanches in the Indian Himalayas. I'll show you brief visuals of some avalanches and some kind of hazards in cryospheric regions, so that you can visualize what kind of situations are there. See, this is a full depth avalanche which is coming. The visual has been taken from about 10 kilometers from the actual avalanche area, and you can see the amount of snow which is rushing down. You can see the snow walls which have been created on the roads in these areas. This is the Jozila Pass area. The height of the snow wall, it extends from 4 feet to 7 feet. This is the crevasses which are there in the various glaciers. These crevasses have a depth of around 2 to 3 kilometers down, and the temperatures at the base of the crevasse are even lower than minus 40 degrees centigrade. This is the crevasse ladders which are being used for crossing the crevasses. This is the glacier's view. This is also a complete visual of the avalanche. which has occurred in Gulmarg area. You can see how the snow mass is moving down. I'll give you the various figures of the speed and the force it exerts in the upcoming slides, but you can see the amount of snow coming down and what kind of impact it can have on whatever human establishments or infrastructure is there on its way. This is a wet snow avalanche. Wet snow avalanche occurs when the moisture content in the snow is more than around 30%. So it moves very slow, but the weight of the snow moving in this avalanche is quite high as the density due to the moisture content is quite high. You can see here the movement is from here. It started from the top zone and it will come to the bottom of the area where the human establishment or our Indian Army establishments are there, giving it an enormous shape. As you can see here, right, starting from this place to this place, the volume of snow has increased around 10 folds. Like this one. So you can see whatever establishments would have been in this valley would all have been destroyed by this kind of avalanche coming to the valley and just blocking the river here as well as doing damage to all the infrastructure in this area. So avalanches, what are avalanches basically? As a historical view, avalanches were considered or imagined to be as giant snowballs which increased in size from accretion of underlying snow. You can see they were depicted as such kind of snowballs, and while coming down, the accretion increased and the snowball size increased. Same is the picture here as well. So avalanche is something which comes like a sudden downward motion of snow mass, which may contain rocks, soil, ice, trees, etc. Velocity of avalanches is 80 to 300 km per hour, and it exerts a pressure of about 50 tons per meter square. It can be channelized or confined. It may travel as a coherent block or disaggregate into small particles as well. Different depictions of the avalanches are shown here as well. What drives the avalanches? So the first question is, when it takes such a big shape and such a big size along with such a velocity and kind of mass motion, what is happening? What is going to drive this? Driving force is gravity. So you can see from here, it is going down. The basic driving force is gravity. Gravity is basically a force that attracts the object towards the earth. So the total force of gravity is given by the formula which Newton has given us beforehand. Now, the factors affecting the avalanche release. There are three factors on which the avalanche release depends. So broadly, they are: first is the terrain, you can see, which is fixed, which cannot change. The snow precipitation, which is the variable. I mean, different seasons have different types of snow and what kind of snow buildup or snowpack has taken up. And the weather, which governs the settlement. In the first slides of snow, I showed you there are different kind of snow crystals which happen with time. So it depends on the type of weather after the fresh snowfall has occurred, what kind of weather is there, which governs what kind of snow crystals will form. Different type of snow crystals will have different type of density and different type of weight, which depends on the formation, which will influence the formation of avalanches and the trigger for the same. In 1998, the province, a Canadian weekly, gave a basic formula for avalanches. So they said that avalanches occur when snow on mountain slopes becomes unstable. Slab avalanches, they come with a velocity of 300 km/h. Solid snow breaks, loses, splits into pieces as it slides. It is shown here in the figure. The other type of avalanches they decided was the dry snow avalanches. 160 km/h is the approximate speed. Powdery snow and wind mixture which comes, and the third type is the wet snow avalanches, which have a velocity of 80 km/h and mass of wet and dense snow is moving down like a river. Slab avalanches often occur on convex slopes, breaking the ice crests, as is seen here. So conditions which are conducive for the formation of avalanches are: the slope should be 30 to 45 degrees slopes, snow accumulates and gravity makes it unstable. Steep slopes, the snow slides and will not accumulate, so it will not lead to avalanches. And low angle, the snow becomes stable and avalanches don't occur. So after this Canadian Weekly, there was so much of research on the type of avalanches, the runout and the potential damage which they can cause. So as of now, there are four type of avalanches which are considered. First is called a slough, which is small snow slide that cannot bury a person even, though there is a danger of falling. And potential damage is very unlikely, but the possible of risk of injury or death to people is there. The physical length is less than 50 meters. Volume is less than 100 meters per cube. Small avalanches, it stops within the slope, won't bury, injury, or may kill a person. The length is less than 100 meters. The volume is less than 1000 meter cubes. Medium avalanches runs to the bottom of the slope, could bury or destroy a car, damage a truck, destroy small buildings or break trees. The length is less than 1 kilometer and the volume is less than 10,000 meter per cube. Fourth is the large avalanches. They run over flat areas significantly less than 30 degrees of at least 50 meter in length, may reach the valley bottom also. Could bury and destroy large trucks, trains, large buildings and forested areas. The length is greater than 1 kilometer and volume is as high as 10,000 meter cube. So avalanche types, basis of releases of avalanche are: either there is a point release which leads to loose snow avalanches. They basically start at a point in loose cohesionless snow. Downslope movement entrains snow from sidewalls. In dry snow, they are relatively small. In wet snow, they can be large and destructive as well. Slab avalanches, layers of cohesive snow may fail as a slab itself, can be triggered from below. Fracture must occur at the crown, flanks till the toe, depth, and controlled by depth of failure of the plane. Basic snow cohesiveness, as per the basis of snow cohesiveness, the avalanches are categorized into dry snow and wet snow avalanches. Loose snow or slough, as I've already discussed, generally occur at the surface of the snow. Snow type is new snow or wet spring snow, spreads from its origin point. Sloughs seldom move enough snow to bury a person deeply. Potential danger to winter recreationists by being pushed over a cliff or a rock band. Slab avalanche, you can see here in the figure, this is the fracture crown. The total slab moves as a complete unit. There's the weak layer which causes the fracture. There's a layered snowpack. You can see there are two different layers of snow between which there is a weak layer which has caused the fracture, and the slab has started moving from here. So various points in the slab avalanche are: first one is the trigger point where the trigger happens. Second is the starting zone. The third is the crown where the slab breaks. Fourth is the flanks. Fifth is the bed surface. Sixth is the stotch wall. Seventh is the track which it follows. And eighth is the runout zone or the debris store. As on date, there are three paths of an avalanche which are being decided as per the experts. First is the starting zone, which has a slope of greater than 30 degree, which includes the crown face and starting of the bed surface. It ends at the stotch wall. The second is the track, or we can say the avalanche path, which has a slope of 12 degrees to 30 degrees. The last one, or the deposition or the runout zone, which leads to the debris deposition at the toe of the avalanche. The slope is less than 12 degrees. This is the total avalanche path. Various type of avalanches, the figures have been given here. First one, you can see it is a slough. Second one is a powder avalanche. Third is a powder avalanche. Fourth is a powder avalanche. Fifth is a kind of a powder avalanche and a slab avalanche combined. Sixth and seventh, you can say they are both the wet snow avalanches. What are the implications of avalanche hazards? Dams and small rivers initiates rockfall. It destroys the forest, erodes the snow cover, damages the hill roads. It affects and disrupts winter sports, tourism, communication, on-foot movement, vehicular movement, hill development, and obviously the military operations in our kind of scenario. What are the challenges faced in handling of these kind of avalanches? First is the rugged mountain terrain, which is very rugged and harsh. Inhospitable weather conditions for people to go there and study the formation of avalanches. Poor accessibility in times of snow. Very limited working season because it becomes very cold or snowy. Data scarcity, there is very less amount of data available as on date for these kind of studies. There is large spatial and temporal variability in these kind of areas. So first very thing to avoid the avalanches is live in harmony. That is the first thing which we as Indians, we advocate also. So we prevent the interaction of human with the snow-covered peaks so that the avalanche doesn't occur. So this is done by avalanche forecasting. We forecast it beforehand and we tell people that we should not venture into these kind of areas when the avalanche forecasting has given a medium or a high danger. Respect nature, generate awareness between the locals and other people so that they should not venture into these areas when the slopes are ripe for the avalanches. Choose very safe zones. Hazard mapping is a process in which various zones of various mountain regions are marked, which are proven to be hazardous and potential avalanche threats. So these safe zones are marked and unsafe zones are marked, and it is made clear to the people that they should not venture into the unsafe zones during these seasons. Harvest snow. There are various control structures which are being implemented so that the snow stays over and it can be harvested into water in the summer seasons. Avoid massive release. Massive release of avalanches with artificial triggering should be avoided. Retain snow in the formation zone. Snow control structures we should implement. Divert snow, the middle zone, snow control structures, arrest and spread. Runout zone control structures. Stop tree cutting. Afforestation is one of the source with which we can bind the snow to the mountain slopes and which can help us prevent avalanches. Avalanche release is a result of various processes spanning a scale of around 0.1 microscale, 0.1 mm to around 100 meters. In the micro scale, we have to study the material as a snow, as I've already shown you the various types of snow crystals which occur during the snow formation, the snowpack formation. Here you can see the avalanche release can be studied with these kind of snow structures. With the snow structures we can find out what kind of the snow crystals will be forming and whether it will lead to some kind of breakage between the various layers or not, or what kind of layers will be forming. Second is in the spatial variability, the physical process modeling, right, starting from the material, it goes to the layer level. In the layer level, what we do is we do a stratigraphy technique in which we put a cut in the snow and then try to define various layers in the snowpack, as you can see in this figure. And then we try to define what are the weak layers in the snowpack and what kind of effect these weak layers can have and which can lead to slab avalanches. Engineering analysis and solution, we go towards the slope scale in which we try to find out what kind of slope scenario are there, what kind of wind conditions are there which can lead to an avalanches. From there, we go to the snow hydrology part and basin to regional scale in which we apply the avalanche forecasting or the mathematical modeling as weather forecasting to these areas to predict the avalanches. And then we go finally to the mountain ranges, that kind of spatial variability where we use the terrain and snowpack information combined with the remote sensing data to predict and forecast the avalanches. Understanding the cold stress. Workers which work in very cold environments for sometimes for extended periods of time, or cold stress sometimes for extended periods of time and sometimes in kind of stress or warlike scenarios, the cold stress is a common problem. The four factors which lead to cold stress are cold air temperatures, high velocity air movements, dampness of air, contact with cold water or surfaces. The cold will force body to work harder to maintain its temperature. Cold air, water and snow all draw heat from the body. So the body temperature goes down. In a cold environment, the body's energy is used to keep the internal temperature. Blood flow will shift from extremities to the outer skin to the core, increase risk of frostbite and hypothermia. So now coming to our erstwhile lab snow and avalanche study establishment, our vision is to be a center of excellence in cryospheric science, engineering, and facilitate high operational mobility in Indian Himalayan region. The mission is to provide precision avalanche and mountain weather forecast support to services, including advice on avalanche control structures, enhance cryospheric hazard forecasting capabilities through systematic data collection in cryospheric region and creation of cryospheric information system. So we are basically unraveling and engineering the cryosphere. The core competence of our lab is mountain hazard and assessment and forecasting, mountain hazard mitigation and engineering solution, snow mechanics and material characterization, cold region instrumentation and sensor design, remote sensing application in snow and avalanche studies using satellite and airborne platforms, numerical and statistical data analysis techniques, and modeling and simulation. First areas are operational avalanche forecast, design of strategic avalanche control structures, applied research in snow mechanics and physics, computational snow material science, snow cover information system and mountain hazard mapping, instrumentation and instrumentation and sensors for snow and avalanche research, snow climate research and mountain meteorology, training on avalanche safety and rescue. Compulsions of staying close to the avalanche prone areas. So a basic question arises, why are we in a compulsion to stay very close to the avalanche prone areas when we can avoid them by going away? We have to have the border vigilance in these areas. There are health resorts in these areas, refuge in the hills, maintenance of habitats and facilities, cash crops are there, winter sports, tourism and mountain adventures. Seed cultivation is there, herb cultivation is there, various research centers are there, and trade with neighboring countries also exists in these areas. There are two types of methods of avalanche mitigation. First is the active methods, in which first very effective method is the controlled release of avalanches. When our model says the slope is ripe for the avalanche, we trigger the avalanches by artificially trigger the avalanches with the explosive, which has a very specific timing. The structural control, in which we put some various snow control structures which arrest the avalanche formation. These are expensive. Afforestation, which is also expensive and a long-term phenomenon. The passive avalanche control mitigation methods are, first is the forecasting. which is the general mathematical model forecasting, which we are following as of now. Mapping, which has rapid turnover, and awareness to the army by spreading awareness and making people aware that they should not venture into the avalanche slope when the slopes are right. So again, mitigation measures, they can be classified as two types, temporary and permanent. Temporary is avalanche forecasting and artificial avalanche triggering. Permanent is avalanche hazard mapping and avalanche control structures. So our SASE's network in various Himalayan ranges for avalanche forecasting is in this way. The Karakoram range, Shamshabadi range and Great Himalayan range, we have 41 field observatories, 15 sector observatories, 3 principal observatories and 43 automatic weather stations. And we have prepared at least for Chaukiwal Tangdar access, Nunkan access, Baltal access and Siachen Glacier access. Operational challenges, I have shown the operational challenges as a figure here. We have vast, rugged, snowbound mountainous areas in which we have inhospitable weather, poor accessibility, human effort is there, demotivation of humans is there, land survey time and consuming point data, it's very tedious, atmospheric attenuations, radiometric corrections, and revisit time of satellites is very high, difficult due to modifications, non-availability of air support when required, limited data and observation points, and data scarcity of these areas, large variability, spatial and temporal distribution, and frequent movement in these areas by the Indian Army. So in the map, you can see we have 41 observatories, as I've already told you, which are more or less, towards the actual line of control. We have some observatories in Himachal Pradesh area also. Now we have started in the Uttarakhand as well as the northeastern areas also. We have 3 principal observatories in HP sector, which is the Solan, Dhundi and Petsu area. And we have around 43 AWS, which are all spread in Western Himalayas Assam State. This is the spread of the automatic weather station network. You can see most of the automatic weather station, they are towards the line of control area where our troops are deployed. One of the picture of our sector observatories, this is Gulmarg, this is Thundi. Gulmarg, Dhundi, this is Kanzalwan, this is one of our automatic weather stations installed at 2440 meters. So what is the field data requirement for the avalanche forecasting? Basic classes of field data are, first is class 1 data, which is given by the shovel test, rush block test, collapse test, shear frame test, and ski test. These are the direct tests which are giving a direct inference for the slopes to be ripe for avalanche forecasting. Second is the stratigraphy data. As I've already shown you, we make a pit in the snow, and then we start studying different layers of snow and the density profile, and we find out is there any kind of weak layer between the snow which can lead to the avalanche formation. We have also been doing the automatic snow stratigraphy, in which we don't dig a pit, but we have a snow micropen which with a penetration speed of 20 millimeters per second and a layer resolution of 1 mm. You can see one of our scientists is using the snow micropen which goes into the snow and gives us various information about the different types of the snow crystals, the hardness profile, and various other things which see, this is one of the output of the snow crystal with depth and what kind of force it has to exert. The kind of force which the snow pen has to exert getting into the snow gives us an idea of about the strain bearing capability of the snowpack layers. The third data is the meteorological data, which is called the class 3 data. SNOMED data availability, we have availability of around 40 years of SNOMED data for J&K, Himachal, Siachen and Uttarakhand. You can see most of the stations, we have minimum data available for more than 5 years, but there are a few stations in which we have data available for more than 40 years as well. Coming to the climatology of the Indian Himalayas, this is the climatology map of the Indian Himalayas, which shows three basic things: the seasonal snow, the maximum standing snow, the highest standing snow, and the temperatures. So in the Shamshabadi range, the temperatures go up to -1.3 as average temperature. The standing snow goes up to 139 centimeters. The seasonal snow goes up to 1022 centimeters, and the highest standing snow has gone up to 245 centimeters. Similarly, for the Pir Panjal range, the total seasonal snow is 740. The standing snow is 111, and the highest standing snow is 183. Similarly, for the Great Himalayan Range, the highest standing snow is 235, the total snow is 547, and standing snow average is 102. And when it goes to the Zanskar range, the figures are down. But again, in this climatology, I would like to highlight one point. You must be seeing that the total seasonal snow is 1022 here, but the highest standing snow is 245 and the average is 139, while the highest standing snow in the Ladakh range and the Karakoram range is quite high. The reason is due to lower temperatures in these ranges, the melting at these ranges are very slow, and which leads to the more deposition of standing snow in these regions than in case of Shamshabadi and Pir Panjal ranges. So flow of data, we have various field observatories. From field observatories, the data flows to the sector observatories, from where it flows to the mountain met centers. Mountain met centers send this data to our operational and weather forecasting system, which gives final operational weather forecasting to media, state disaster management authorities, and national disaster management authorities. So the farthest unit is the field observatories or units. Then it comes to sector observatories, army formations. Then it comes to the mountain met centers, and from there the data is given to NCMR, WF, IMD, and SASE. We have a cold laboratory in which we have a cold chamber in which the temperature goes up to -40 degrees centigrades, where we study different kind of snow. So we study the snow mechanics as well as the snow physics in this lab. Snow mechanics gives us the idea about the failure criterion, constitutive laws of snow, and mechanical properties of snow. While the snow physics, we study the structure properties of modeling, heat and mass transfer, snow metamorphism, meltwater percolation, and snow cover stability. Coming to the passive methods, avalanche forecasting, class 3 data is required, which is the snow data and the snowstorm cover buildup, which I have explained earlier. Class 2 data, snow profile test data, identification of weak layers, avalanche occurrence data. And class 3 is the field test failure. Class 1 data is the field test, failure of weak layers, and result analysis data. These all data are combined in a risk assessment matrix, and finally the decision making is done and the dissemination of final avalanche forecasting is done. So this is one of the sample avalanche forecasting which is done. This is the stratigraphy stability assessment. We have also done various training aids, and we provide training multimedia CDs. Avdhav, Ek Vipatti, we have made an animation. Avalanche accident animations we have made, and different posters we have designed to various army and civil population which resides in these areas, so that they can be safe from avalanches. Passive methods, we have been conducting various avalanche awareness programs in Srinagar, Leh, Bahang, Himachal, avalanche awareness cadres in Kupwara, Dras, Base Camp, and Palchan. We also provide training on field tests to various military people who are there in these areas, so that they can themselves assess what kind of danger is there in these areas. Active methods of avalanche control. In Badrinath, we have provided mounds in the runout zone which save the temple from the avalanches. We have given various formation zone control structures at Banihal Top, D10. We have been actively involved in the artificial triggering of avalanches in these areas. Formation zone control structures, these are the snow racks which arrest the formation of avalanches right starting from the top of the formation zone. It holds the snowpacks, it inhibits avalanche initiation, longer retention of formation zone snow melting process is slower down, lower temperatures, gradual release of water downstreams. Formation zone snow control, the structures is the snow nets as well. It has a flexible structure. It is easy to assemble, holds the snow in a mesh as is seen here, retains the snow longer than the snow season. Artificial triggering, as I already told you, we use a RL gun and artificially trigger the avalanches with the explosive. Runout zone control structures, these are various snow galleries which have been designed over which the avalanche can pass and the road can be safe. This is the snow gallery at South Portal approach road to Rohtang Tunnel, Dhundi. Snow gallery at Manali South Portal 8, snow gallery at Manali South Portal 9. Avalanche controls, diversion walls and mounts. As I've already told, this is the Badrinath temple. These are the mounts which have been designed by Sase, and the diversion wall which divert the avalanches and arrest the avalanches so that they cannot destroy the temple. So avalanche incidents. So avalanche incidents in various sectors and how many people have been dead, they have been given in this slide. In 2019, 10 people were caught in an avalanche in Khardungla Top. Similarly, in Banihal Kazigund Access 2019, 8 people have been dead. Namgya, 6 people have been dead. So these are the incidents which do happen when people don't adhere to the warnings or the avalanche forecast which have been given. Avalanche incidents in 17-18, they have been quite low as compared to the 19 incidents. So in 2012-13, there was a lot of casualty in the avalanches. 10-0-15 avalanches were there and 13 casualties were there, after which the training on avalanche awareness was taken up on a larger scale, which has a direct impact, and we are having a low impact on the we are having a low disaster from the avalanche hazard. Dissemination avalanche alert, which is generated by SASE, is given to SDMA Himachal, SDMA Uttarakhand, SDMA J&K, and Northeast as well. So this is the avalanche dissemination formats which we normally give to the NDMA as well. Various things. So coming to the sensors or the indigenous sensors which we are coming up for these kind of areas, because the sensors are not actually available off the shelf for these areas. So we have taken up a project called Automatic Low Cost Snow Meteorological Observation System, which is called the LCOS. The need of the project was there was heterogeneous hardware L1 based which was bought over the years, and we wanted a layman operable hardware for these areas. And we wanted to have a system which will have DIB configurations, many-to-one communication alternatives like VSAT, GSM, and satellite modems. Our objective was development of state-of-art autonomous system with reliable data loggers, snow-specific sensors suited for SASE's area of observation, and operationalize a network of automated, low-cost snow met observation system in different climatic zones of Indian Himalayas, in which we have started, and we have already started to put up a patent of this kind of sensor, which is a reflective snow depth sensor, which we have fabricated in our lab and we have deployed and we have already tested in these winters. Because the ultrasonic sensor which was available off the shelf, it has various issues. So the idea was conceived of a proximity snow depth sensor, and fabrication was done and lab experiments and trials have been conducted. This sensor basically consists of a retroreflective sensing module, which is designed, and 25 pieces of a PCB are made, and it has been deployed here in Dhundi. Basic design says that all of these sensors will not be switched on at one go. This sensor, it will just sense the snow in front of its face and give an output. So it is made in a modular form, as the power is a constraint in these areas, and the microcontroller switches on one sensor at a time and keeps on reading all the sensors so that we get a fair idea of what kind of standing snow is there. The second snow sensor which we have developed is the snow water equivalent sensor, which was basically done with the help of snow pillows, which were large metal sheets with the antifreeze liquid, which was very difficult to transport to these areas and fit in. So we designed a snow water equivalent sensor with load cells and used Zemic B11 capacity 350 kg load cells. We made a load bearing structure, 4 load cells mounted onto that structure. We have already tested this sensor also, and we are getting quite encouraging results as compared to the manual observations in these areas. We have also designed a snow temperature profiler in which we had a Mark 1 of this, in which we had thermistors reaching out of a snow pipe so that we can measure the temperatures of various layers of snow, which had some issues in the first go. Now we have come with a Mark 2 version of the snow temperature profiler, in which we have thermistors which are straight mounted, and we have already used this in the field, and it has given quite good results. It is successful and the deployment has been started in the field. We also have a snow telemetry network of the automatic weather stations, which with the aim of continuous availability of real-time snowmelt data from SASE's snow telemetry network of 60 automatic weather stations. We do the detailed planning for operation and upgradation. We do the liaison and coordination with the Army for logistic support. Training and online help is provided to Antarctica team for members. And we have done the failure data analysis for various sensors to plan the timely replacement of AWS sensors. Uninterrupted data for operational avalanche forecasting is given with this network, and performance estimation of automatic weather station parts for planning and replacement is there. So we, as an example, we have drawn the reliability curve for the snow depth sensor, which follows a constant hazard model, and we have also derived the mean time to failure from the experimental value, which is almost matching the estimated value with this model. We have developed a glide shoe, which gives the gliding movement of the lowermost part of the snow, which gives a direct inference of how the snowpack is moving. This glide shoe, we have utilized a draw wire sensor, which is installed at the slope. This draw wire sensor has a shoe type structure made on which the snow accumulates, and as and when there is a movement between the earth and the snow surface, it draws the wire and gives us an output as a linear sensor. Last but not the least, how to survive in an avalanche. Jump upslope, move to the side of the avalanche, hold onto something, swim to stay near the surface of the avalanche, because once you get buried, it will be difficult for you to breathe. Give yourself some breathing room if you're going to be buried. Create an air pocket near your nose and your mouth. When the avalanche slows down, but before it stops, cup one of both of your hands in front of your mouth to create an air pocket. With a small air pocket to breathe, you should have enough air for at least 30 minutes to survive. Take a deep breath before the snow settles. Right before the snow settles, inhale deeply and hold your breath for a few seconds. This causes your chest to expand, which will give you some breathing room when the snow hardens around you. If you don't have this breathing room, you may not even be able to expand your chest to breathe while you are buried. Air pocket. Any space around the victim's nose, mouth considered to be an air pocket. Difficult to determine presence with digging activities. If no snow in upper airway, then consider an air pocket is to be present. Conserve air and energy. If you are very near to the surface, you may be able to dig your way out, but otherwise you aren't going anywhere. Don't waste your precious breath by struggling against snow. Remain calm and wait. If you hear people nearby, try calling them, but don't keep it up if they don't seem to hear you. You can probably hear them better than they can hear you, and shouting just wastes limited air supply. 4 phases of avalanche survival. Survival phase, first 15 minutes is 93%. Air depletion phase, first 30 minutes, 2/3 of the victims die. And waiting phase is 45 minutes to rescue. 4 phases hypothermia begins when the body temperature drops below 35 degrees centigrade, and it is extremely rare for a victim to survive once the body temperature drops below 29 degrees centigrade. The survival phase is critical when the body is cooled. It will divert blood from extremities to the vital organs. When body is warmed, blood will return to the extremities, but at too low a temperature, this will cool the vital organs, causing death by thermal shock. Avalanche rescue and safety equipment. There are various avalanche victim detectors which are being used, which are class of emergency beacon locators, active radio transmitters operating at 457 kilohertz. It is a specialized frequency which is for this purpose only. Worldwide it is being used. Shovels and avalanche probes. So that's all from my side. Thank you very much. Thanks for your patient hearing. Can you hear me?
Yes, sir. Thank you so much, sir.
Thank you very much, sir.
If any questions are there, they are welcome. I think if there are no more questions, I'll take your leave.
Sir, please wait. Sir, please wait some time. Someone has asked a question.
Okay.
I think someone has asked meteorology and metrology. The difference between meteorology and metrology.
Actually, meteorology is basically a measurement science which deals into measurement, while meteorology, it is. Can you hear me?
कहाँ रखने का बता जेब में है तेरी जगह
Hello, can you hear me?
Yeah.
Sir, for detecting this avalanches at your experimental level or on at a natural disaster monitoring, what specific type of transducers are used?
If you have gone through my presentation, in the
Yeah.
last leg of my presentation, I have shown you three basic measurement is of snow only. So we use snow depth sensors, the snow water equivalent sensors, and the snow profile temperature sensors.
Okay. Thank you, sir. Thank you very much. Very nice presentation, sir. Thank you very
Thank you,
much.
ma'am.
Yeah, sir, there is any other questions?
Dynamic range sensors. Can you explain what is this dynamic range sensors?
Sir, Sarma sir, thank you so much. I think, sir, you have explained very well and simple manner sound sensors and transducers. I think there is no question. If there is any question, then we will reply via mail.
Yeah, no issues. I am available on my email. I'll send my email here itself on the chat box.
Yeah, sir, I am requesting to, if you send your presentation, then this will be helpful for others and
Actually,
us
this
also.
has some maps in the present. I have some maps in the presentation. I need to take them out. Then I'll share it with you.
Thank you, sir.
Okay. Thank you so much.
Thank you, sir. Good day, sir.
Good day.
Thanks
Thank
to
you.
all of you.